All right, should we do some machine learning here?
Sure.
All right. So my goal. Oh, last night, I was flipping through my science blog, and I saw that Alpha. You might have heard of AlphaGo. They're in Britain, and they did the program that won against Go, and they have just finished the thing called AlphaFold, which is supposed to be absolutely a huge movement forward for medicine because it tells you how a protein folds.
Wow.
And they do it using machine learning. But then I looked up self-driving cars, and remember how 3 years ago, they said we were all being self-driving cars by 2020.
Mm-hmm.
And it says, no, it's going to be another 5 or 10 years.
Oh, yeah. Oh, my God.
That's kind of where we're at. All right. So anyway, so what my goal with these slides was to tell people the basics of machine learning whose math abilities are at your level. So if you're not getting anything, holler, right? The future, right? The future is nigh, right? Computers can drive cars and pick criminals out of the crowd, and our world is changing. And will it be good or will it be bad, right? If you haven't read this science fiction writer, he writes some good books, and he basically says science is magic until you know how it works. So I'm a believer, when you're sitting in your kitchen, you should know how the basics of how a car works. You should know basics of how your fridge works and an airplane works. You should know basics how a computer works. All right, so now let's compare. I don't really know how much you guys know, so I'm really just starting right at the beginning here. What's the difference between coding and neural nets? All right. So in coding, this poor grad student sitting in the basement, and he writes some code, right? There's an example of code. And each instruction is written in Java and by a human, and it can be very, it can take so long to write the smallest piece of code, right? And why do we do them? Well, if there's a reasonably easy, simple, repetitive task, you can code it up and you can get it to do it. Like banking, right? You can write all your code for bank. Money comes, money goes, and you calculate the interest. Pretty straightforward. Now, what is a neural net? Well, it doesn't have Java code at all, right? It has this thing called a neural net. And how do you tell? And all the neural nets basically look the same. They all look like this. And how you change them is you change the weights on their edges. Just like in the brain, one neuron fires and it might get another to fire. It's all based on the weights of the edges, right? Now, who understands these weights? Nobody. Nobody understands these weights. So how do you get the weights? There's a very simple algorithm which you give it a lot of data and it learns the weights, all right? And what it basically does is it finds patterns in the data, right? It tries to fit, it has all this data and it sets the weights to mimic the pattern of the data, all right? So now let's say we have some more complex thing, like not banking, but we're trying to learn to get a robot to walk, right? And we could say, hey, we're such good coders, we can get our robot to walk. But it failed miserably. In the 80s, you guys, I know you weren't born, but I was graduating high school and everybody was like, AI, it's going to, right? We all said self-driving cars, right? And it didn't happen. Well, I've been there before. Right? In the 80s, they were like, expert systems they're going to solve all our AI problems, right? and in the 80s, and it completely failed. And the reason it failed is because though you know how to walk, how do you tell someone else how to walk, right? Every little nuance of, I have my leg at this angle, then I push with this force. Way too complicated, right? So it's too complicated for a coder to code up. But if you get lots of data of watching somebody walk, then there's a pattern to how to walk, and the neural net can learn to walk. And certainly robots are walking quite fine now, and it's because of neural nets. All right? So the code in some ways is very complicated, and the neural net, well, the weights are complicated, but you don't have to understand the weights. Nobody understands the weights. The algorithm, which takes the data and produces the neural net, is quite simple and quite elegant. And my goal is to tell you at a high level really what's happening here, right? And there are certainly nuances to get it to work, but the math is straightforward, all right? And we can all understand it. All right, so now in red for a while, I might say what neural nets aren't good at, right? They're good at, this just says, what are they not likely to be able to do soon, right? They're not likely to solve great, complex, deep understanding problems soon. They're not going to have emotions and empathy soon, right? They're not going to have consciousness soon. All right, let's go back to when I was a graduate student. I started graduate school in 87. All right, 87. What was your parents doing in 87? Maybe they were starting graduate school in 87. Anyway, then the big hot topic were genetic algorithms, right? How did Darwin said that things evolved, and how does that happen? Well, a genetic algorithm is we're trying to solve some problem, and we can have a population of possible solutions, right? Maybe we're trying to solve in fact, when I was a graduate student, there was another graduate student at U of T who wrote this fantastic animation program which got little beings to walk. And it was groundbreaking, and he got lots of gold stars and a job at U of T. So how he got it to work was using this genetic algorithm, right? You're trying to figure out how to control your robot, and so you have a whole population of possible solutions to controlling your robot, right? There's our robot over there. There's a family of possible solutions. And what do you do to your solutions? You add some random stuff, and you take various solutions and you cross them, right? This was a good solution and this was a good solution. So we will just sort of take half of this solution and half of that solution, right? And now you have a new population, right? We randomly changed some, we randomly mutated some, we mixed some, and then you keep the best of the best, and you repeat. And you keep doing that, and your solutions get better and better and better. And that's exactly what Darwin said happened, right? So there's a complete parallel here between evolution and these genetic algorithms. All right, what's supervised learning is when you have a supervisor telling you the answers, right? You have lots of questions, and the supervisor will tell the machine learning the answers. And so that's just what I said here. Supervisor tells the machine, right? So in general, we have some system that behaves a little well right now, but not so well. It starts off being a very bad system. but you have a supervisor which gives feedback and says, hey, you got some mistakes here. You need to fix these mistakes. And the way to fix these mistakes is to head in a certain direction, right? And then the system changes its parameters and moves in the direction to according to how the supervisor told the errors were, and the system gets better and better. And so it's kind of like gradient descent. You have a machine, an algorithm that's sitting here. The supervisor says, they're mistakes, head in this direction. And you keep following the direction the supervisor tells you to go until you're sort of at the bottom of a valley, and that's what your algorithm will be.
Sorry, I have a question about that.
Yeah.
So is it kind of like, because I was doing some reading on AI before, and it's like there's like a punishment usually.
Yeah.
And then what they try to avoid the punishment by, well, we feed them more data and they try to do better, right?
Yeah.
Okay.
Reward, punishment, you direct them. You just give them a little help into which direction to head.
Okay.
Right?
Yeah. And the genetic algorithms, right? The solution space, does it get smaller or does it get larger as you keep on going down the...
Usually you'd have your population space be as big as your computer can hold.
Okay.
Right? It's depending on your running time. You want to really, if you know any environmental hippies, they want to save as many seeds as possible, right? Crops, the farmers want one monocrop, but we know the way to keep life going is to have a very broad population of diversity, right? And so you want to keep a big population, and within that population you mix them, and it's survival of the fittest. So you kill off things that aren't very good, but you do it randomly. The worse you are, the higher the probability is we kill you.
Gotcha.
Right? The better you are, the lower the probability is we kill you. And then we evolve, right? That's how, if you didn't run that fast, then there's a higher chance the lion eats you, right? That's how evolution works. So this just says, you take any system and you give it feedback to put you in the right direction. And you add a little randomness, and what emerges is just awe-inspiring complexity, right? And here's our supervisor. She just says, yes, that's a bicycle. No, it's not a face, right? That's the kind of thing a supervisor will do. And what evolves is AI. Right? This is a picture from Michelangelo, God and Adam. All right. So there's sort of layers of complexity that's happening, right? At the bottom layer, our brain are just these simple neural nets. And kind of, if you change the weights on the neurons, then you get human life and you get love. Right? And then at the bottom here, we have these simple neurons, which you change their weights, and out you get a neural net from which you get machine learning, right? So it's the same sort of thing happening.
So
and we don't understand love, and we don't understand the neural net, but it comes out of these simple processes and a simple learning process.
Sorry, so out of the population of solutions, there's one that comes out of it. There's one like perfect solution that comes out of it.
Let's actually, I was talking about genetic algorithms because they relate to evolution, and they were the popular thing in the 80s. But that's not what we're going to talk about today. Today we're going to be talking about gradient descent, where you always have one solution. We're going to keep one solution, and we're going to move that solution through the solution space.
So it's that same solution, just improving on itself, right?
Yeah. Yeah, we're not going to be doing populations of solutions today.
Okay.
All right. And here, just the point is, we don't understand love and we don't understand the neural net. Somehow it's a deeper, complex thing than we can understand. Right. And personally, if you talk about religion, I sometimes wish I had more spirituality. You know, I see people who have spirituality and beliefs, and I'm an agnostic, so I don't know what to believe. But one thing I do believe, and I find oddly spiritual, is that if you have some really simple process where you give it feedback, then what will emerge is complexity beyond our comprehension. And that's kind of a spiritual thing, right? And if you ask, where did we come from? In some ways, that's where we came from, right? If you believe in evolution, right? Even if you believe in God, well, you might call this whole process God, where out of simple things emerges complex things.
Hey, so I just wanted to ask, I'm a little bit confused. So if you have a neural network, are you pretty much like, let's say you're like a developer or something like that, are you building up like the individual parts and then contributing it to the neural network?
No.
Oh.
We're going to talk. Why don't you wait until I get to future slides?
Yeah. Okay.
All right. We're going to get there soon, right? I just wanted to get the high level what's happening here, right? Machine learning what is machine learning? It's programming computers to optimize their own performance using example data and past experience, right? So what's this? If you do a Google search, which I guess I did, for what is machine learning, here's the definition, right? You get your computers programmed so that they can optimize their own performance. And how do they optimize their performance? They look at data and they look at their own experiences. That's machine learning, right? And when does it succeed over standard programming? Well, when humans are unable to explain their experience, right? Humans can't explain how to walk, or when there's just so much data, right? When there's so much data and the humans can't look at all that data, right? Now, since the 80s, AI has gotten so much faster. And everything I'm going to teach you today, I learned at U of T. You might know that Geoff Hinton, who developed it, was a professor at U of T. And all the mathematics for this was in the 80s already. So what's changed is we have better algorithms. Are there better algorithms? No, pretty much there aren't better algorithms. There's a little tweaking, but pretty much it's the same algorithms. What do we have? We have more data and we have faster computers, right? One thing that I think is funny, these things called GPUs, graphical, programmable, I don't know what it is. Anyway, what was it made for? It was made for young geeky men to play video games all day, and it's a processor that can do these parallel video game screen stuff fast. And why do I have it on the screen here? Well, having this cheap, fast parallel hardware allowed the AI coders to be able to develop their algorithms because they run really well on these big, fast, cheap parallel processors. All right. So now let me just do a little bit about the world. Is the world going to be better? I certainly hope so. Right. If we don't kill ourselves with environmental problems and war, we could have cool technology. Right. There'll be self-driving cars. It's able to process images now faster than grad students can. It's better and better at speech processing. Medical experts, like it can now find tumors in your in your X-ray better than an expert can. It can now tell you how your proteins fold, right? Legal and medical experts, financial experts. I just bought a bunch of stocks in a robo thing where some robot is choosing what stocks for me to buy. We have robots and and art. The machine learning is building better and better art. So certainly cool things are happening, right? In 96, you might not have been born then, IBM was the first to beat the masters in chess. And that wasn't so impressive because they just used big computers to do a search down the search tree to maybe 7 moves ahead and see what it could manage, right? And then 2011, IBM won at Jeopardy. You might have heard of that. And then 5 years ago, AlphaGo won at Go, which people thought that wasn't going to happen for a long time because Go is a very hard game. I just watched a documentary of this guy right here realizing he was going to lose. Quite a amazingly moving documentary, as the coders realized they were going to win, and the expert Go players learning that they were going to lose. And then what I think is cool, 2 years later, AlphaGo started over. In 2019, AlphaGo learned how to play Go by watching how humans played, right? But then they threw all that away and they just told the AlphaGo the rules of the game, and they got it to play by itself, and it did better than all other programs. It's just incredibly how well it's doing now. And so this is the same people who just last night found out how to fold proteins, which I've always known to be a huge problem. And what I think is cool about this is that there was no human intervention, right? The machine learning learned how to do it all by itself. It wasn't us humans teaching it how to do it. It was learning by itself. So then 2 years ago, I watched IBM do a debate. And what I personally found was that the machine was good at giving arguments, right? What happened is they gave the machine, and both of them, a topic at the last minute, and they could both read up on Wikipedia and stuff. And then based on this the debate question and reading Wikipedia, IBM Watson gave an argument for why, debating. So that it did very well at. What it didn't do well at was counter-arguing what their opponent said. What I've been told, I read this slide in 2018, that Warcraft, it's a video game that my nephew plays. And
StarCraft. StarCraft. It's not Warcraft.
Not StarCraft, it's Minecraft.
StarCraft. It's quite a complicated game actually. It's very hard.
Minecraft
It's a strategy game.
StarCraft.
It's a strategy game.
Warcraft is a different game by the same
Professor.
developer.
Professor.
StarCraft 2.
StarCraft 2. It's StarCraft 2. It should be.
StarCraft.
2.
2.
All
Double
right.
double eyes.
All
on
right.
that.
So they're still working on. In 2018 they did win. Right? 2018 they did win, and that was a big deal. And then there's this new program, this game here called whatever that's called, Hanubi, where you're trying to cooperate with people, but you don't know what they know, and you're trying to give them little clues. And that people say that might be a next step at what they can do. All right. So what are the various open problems? Computers are really good at labeling data when you have supervised learning. if you tell them that this is a car and that this is a tumor, then it will be better than humans at knowing this is a car and this is a human. But what it's not good is if you don't tell him anything. Suppose an alien just landed on Earth and would look around. What would the alien do? They would say, oh, there's these things that move around. I don't know what they're called, but I know that they move around, and I know that they stop when they come to these things that are red, right? So getting a program learn that all by itself without unsupervised learning, right? Without a supervisor. All right. So Google and everybody said that they were going to have driverless cars any day now, but they stopped. And as I said, I just looked it up. They said it will they say now it'll definitely by 10 years from now, there will be cars picking you up without a driver. And but what's the problem now? How to deal with snow, how to deal with morals, how to deal with customer confidence. All right, art's cool. Here's a piece of art it made. Right, look, it's got a face upside down face and a right side up face. Pretty cool. You can get it to generate new art. This one is cool. You get a program which learns to recognize dogs. All right, so now I have a neural net that recognizes dogs. And then you reverse engineer it. You say, give me an image that it's going to most say looks like a dog. And here it says this image is the most like a dog. So it's sort of a dream picture about dogs, right? It's dreaming about dogs. All right, what about jobs? So I just searched the internet and I found some slides here. You know, industry is putting billions into it. It thinks it's going to improve the cost, the throughput, the quality, the customer satisfaction. Everything's going to change. You know, we're going to be outside playing soccer and not working, right? We're going to have more and more. It's going to tell us, hey, the traffic's bad. You need to do this and this, right? Now, right now, it's only that red part right there is being used by technology. Today's technology is used by 5% of occupations, but that is going to completely change. Even the most conservative estimates say that over the next 5-10 years, things are going to be automated, right? So a CEO, for example, the technology that we have today can automate between a quarter and a third of what she's doing. And what she's going to do instead, right, she can use her time to do more valuable things like connecting with humans and creativity. So if you're looking for what can you do in, you know, what careers are good, having human skills, having these soft skills are supposed to be good in the future, right? This just says the various careers, how much are getting replaced, right? So right now, technology can get rid of most of financial traders, a third of legal work, 20% of medical work. Look at that. Isn't that horrible? A third of the work done by your professor could be done by a computer. All right? It says most medical people think that patients will be better off because of this. Right? So what about scary applications now? All right? The problem is people might lose their job, right? Really, everybody could be out of work. And I'm hoping that there'll be a basic income to give everybody some work. How else might be scary? You have, do you want the world customized for you? Do you want ads geared at you? I think that's great, but, right, who's watching you, right? Cybersecurity, right? What happens if somebody hacks into your self-driving cars? So judges right now are deciding who gets a mortgage and who gets out of jail. But are they fair? Do we understand the decisions they're making? Right? China is particularly good at picking criminals out of a crowd, right? But your criminal might be my activist. And then we have machines that are good at killing. Anybody know what's wrong with machines that kill? I'll tell you. The problem with them is everybody wants one. That's the problem with them. And who are they going to kill? Well, you might want one to kill them, but they're going to want one to kill you.
Oops.
And then you ask yourself, who in the world do you trust? Who do you want to be developing this AI? I don't know. It looks scary, right? So it's far more important, right? When I was being born, there was a race to get people to the moon. And now AI is way more important. So if you might want to learn some of it. All right. Oh, I made a new slide and it didn't get on here today. The slide I stuck in here was who I trust is all the hippies who are coding in Silicon Valley. All right. So now that was all my woo-woo slides. And I spent too much time doing that. Sorry. Let's jump in to, was that useful or should we have jumped into math faster?
On.
I liked it.
Yeah, that was
Liked
good.
it.
That was
Good.
fine.
Yeah. It was
All
a
right,
good
so now
like,
let's jump
background.
into some math, right? Our goal is to build a neural net like this. And what is this neural net going to do? You give it a picture and it says face. You give it another picture and it says bicycle. That's a picture of a bicycle with bananas on it, right? And so we have a supervisor and she's going to help you know for the training data what the answers are, right? You had all this slave labor who labeled all this data, and now we know this is a picture of a face and this is a picture of a bicycle. All right, so we have a current neural net. It has weights. This is the best machine we have going, right? It's the weights on the machine, on the edges, that tell us how it works. So you feed it, and how are we going to visualize this? All right. So suppose we only had 2 weights, right? So if we have 2 weights, then we could have a space with the first weight being our x-axis and the second weight being our y-axis, right? And then we'll have our z-axis be, right? So that's what I'm saying here is if we only have 2 weights, then it's a 2-dimensional space. And our current machine is a location, right? You tell me the value of each of the weights, then that tells me the location of my neural net, right? And what the neural net does completely depends on the values of all these weights, right? So we feed in a face, and what does it say? Well, based on all of these weights, based on the location of this guy in this space, right? Then of course we have thousands and thousands of weights. So it's not a 2-dimensional space, it's a 1,000-dimensional space, right? And I feed in a face and it says bicycle, right? And I feed in a bicycle and it says face. And what does our supervisor say? She says, no, that wasn't right. Good try. So we then calculate what our error is, right? How well did it did? How many answers did it get right? How many answers did it get wrong? We count it all up. And based on we're standing right here, based on these are our current weights, our height is going to tell us what all our errors are, right? So that height tells us our errors. Great. Now, how do we learn? Well, we learn by changing our weights. And we're not going to make big changes. We're just going to make little changes. So we're going to increase the weights on those weights that influenced us getting the right answers. We're going to increase the weights. And the weights that sort of influence us getting the wrong answers, we're going to decrease their weights, right? We just look at our right and wrong answers and we change the weights so that it improves just slightly. It does little better than it does before. All right. So here's a direction, right? We're changing weight 1 a little bit. We're changing weight 2, maybe more. That tells us a direction, right? We just sit right here, and from right where we are, we say, how well are we doing here? And what direction should I travel to make things better? And then what we do is we walk just a little bit, right? Here we just moved our machine slightly in the machine space, right? This is the space of all our weights of our neural net. We change our neural net slightly in the direction that would improve the error. And then we're now we're at a new place, right? We used to be there, now we're here. Now we have a new weight 1, we have a new weight 2. So we get here, instead of light green weights, we have dark green weights. So now we have our dark green weights, and we try it again. We give it the Jeff, and it says face. We give it the bananas, and it says face. And then what does our supervisor says? Supervisor says you did better, right? So we measure the error, and here now my error is a little smaller. Here I had a big error, and now I have a smaller error. So things are a little better than they were before, right? And we repeat. And if you think about, for every setting of the weights, right? You imagine in this picture, we have 2 weights. We have weight 1 and weight 2, right? But imagine a 1,000-dimensional space, and for every point in that space, it defines the weights. And so you can imagine putting all our data through the neural net with those weights, and it tells us how well the neural net does. And then the error, how it does, tells us a height. And what do we do with that height? We build a surface, right? The surface space is we call it the error, right? For every way of setting the weights, the height tells us how well the neural net would do. And what we do is we start in a random place, and we get random sets of weights, and we just do gradient descent until we get to a bottom, right? We just keep getting better and better solution, and hopefully in the end we get to the bottom, right? Now you might say, hey, if I'm standing on a hill, why can't I just look over there and say, hey, the solution's over there? Well, why can't you? Well, because imagine you're doing it and you're blind, right? You're a blind person working to climb, to find the bottom of the hill. You're standing on a hill and you're blind. Well, you can't look around. What are you able to do? You're able to say locally where I am, how high is it? Locally, what direction should I head, right? But you got to remember, this is so much computation. There are thousands of numbers here. And how do you know? You have to feed all the data through to know what the error is, right? You feed all the data in to find out what direction should I go to make my thing better. All right. All right. So let's think a little bit about supervised help, right? Suppose this function, see this yellow curve? Suppose that's what I'm really trying to solve, right? I have some input X and I want to find the output Y. Now I'm drawing it as a curve that you would have seen in high school, where the input's a real number and the output's a real number, right? Why did I draw it like that? Because in reality, our function is very complicated, right? The input is an image with the megabits of pixels, and the outputs is a label, whether it's a face or a bicycle, right? So this isn't really a good representation of what's happening over there, but it'll give you some intuition. Does that make sense? So the input here is an image, and the output is it a face or is it a bicycle? And I'm trying to learn that function. I'm trying to learn a function that says, given an image, what should I output, right? And what do I have is I have a lot of data, right? Each point here is one of my training data, right? It says for every integer d, I say I have an image, which is my dth training data, right? And I have the answer. For my dth training data, I know that the answer is that it's a face. And for this other training data, which is a different image, I know that the answer is bicycle, right? So everybody get that the data, the training data represents points in this highly dimensional space, right? Because the input is highly dimensional. X has millions of pixels, and the Y maybe the Y is not so complicated. It's a bicycle, it's a face, right? All right, so what are we trying to do? We're trying to find the machine, right? We have this purple data, and we're trying to fit the curve. We're trying to find a machine, the neural nets. Here, the green defines the weights, which defines the neural net, which defines the curve, right? You know, I'm all about colors. Here, the purple is our training data, are our dots, right? So we're trying to learn this green function that approximates our purple data, right? And when we have a current curve, right? Suppose we have a machine that we like so far. What we can do is we can calculate the error. And how do we calculate the error? Well, it's given our current weights, our current machine, we want to calculate the error. What are we going to do? We're going to do a sum over all our training data, right? We have capital D dots here, capital D pairs, input, output, capital D of them, right? Here, capital D, purple dots. What do? We sum up over all the purple dots, and we ask, what's the difference between the answer the supervisor gave? The supervisor gives the YD, and we give our machine MW with our current weights W, it gives some answer. We ask the difference between them because that's our error on that data point. Then we square it. We'll talk later about why we're squaring it. But one thing about squaring is it makes positive numbers bigger positive, and it makes negative numbers bigger positives. So squaring has that nice effect. And given that, we calculate what our total error is, right? We have a current weights that gives us what our current machine's going to do. We run it through, and we get a current error. And then what are we trying to find? Our goal is an optimization problem. If you took calculus, this is just calculus. We're trying to find weights that minimize the error, right? Given weights, right? Given a set of weights on the machine, we can calculate what does our machine do and what is the error. And our goal is to find the weights that minimizes this error, all right? Now, sometimes, if it's a simple type of machine, if you're doing linear regression, like your machine is linear, then I had a co-op job at Waterloo where I help people solve some optimization problem like this by taking the derivative, and you use calculus to find the weights using calculus, right? But when your program is very confusing, like a neural net, calculus doesn't work. And so instead, you do gradient descent to find the best weights, right? Now, once we find the set of weights that minimizes this, now we want to see, hey, we have brand new data, right? Here's this value X prime. It's data that we've never seen before, right? And we don't have a supervisor to tell us the answer, right? We're now the Google car has gone out into the world and it's driving down the street and it's never seen this grandmother jump in front of it before. And so we want to know how well will the machine do on this data that it's never seen before, right? Right, people, that was the big overview. And if you didn't quite follow it, the next slides, we're going to do it again slowly. Let's see, we went from 2:30 to, oh, we got another hour, don't we? I just checked our time. Everybody good?
Yeah.
Yeah.
All right.
I had a question.
Now, let me give you a little warning about abstract thinking. You guys have all done 2001, so you know some about abstract thinking, but we're going to talk about finding a face, right? We want to build a machine that can know whether this is a picture of a face or a picture of a bicycle, right? And we're going to talk about it with never talking about noses, right? We can build a machine to recognize your face without ever talking about noses, right? And more than that, we might not need to talk about the nature of the machine. Are we doing linear regression? Are we doing neural nets? Are we doing convolution networks? Are we doing binary decision trees, right? There are lots of types of machines, and we're not going to talk about the machine. And the input could be an image, and the output could be, is the bicycle, right? Or the input could be, I'm driving down the street and there a grandma jumped in front of my car, and the output says, should I stop or not, right? So there are lots of inputs, output pairs, and we're not going to talk about them, right? As I said, the image might be a face, but we're never going to talk about noses, right? Now, why do we abstract things, right? We abstract things to focus on what we really want to talk about. We don't want to talk right now about noses or neural nets, right? We want to be able to generalize what we're talking to any model of computation and generalize it to any computational problem, right? So when I go through these slides, I want you to, if you have a question about what I'm currently talking about, then pause me and ask. But if you want to talk about something you learned somewhere else, or you want to talk about noses, then let's not talk about that until we have questions at the end, right? Right? Just try to understand. Every time I say something, try to understand it. Don't think, oh, what should Jeff say? Don't think, what should he be doing? He should be talking about noses. But no, I'm not talking about noses. All right? All right, so we did that fast, and it might have scared you, but let's do it slower, all right? We're going to say exactly what I said in those last few slides, and we're going to do it a little slower. So this time, if you have any questions, holler, all right? So let's review everything we just said. We're given training data. And what's training data? It's a big set of tuples, right? It may be millions and millions of samples, right? And each sample, it has an example input and example output, right? And I can imagine plotting it. Somehow you plot all the various inputs, and for each of the inputs, you plot what the output is, right? So here I'm saying, is what I said already, well, I'm pretending to graph it on where X and Y are real numbers, right? So here X is a real number, Y is a real number. Why do we pretend that? Well, because we're better with real numbers. But each dot, as I said, is a data item, right? It has an example X and example Y, right? And here the deep training data, right? This is the example X, and that is the example Y, right? Now, what is our X really? Our X really is not a real number. It's some big complex image, right? Or who knows what we're trying to learn. It's some weird input, right? And as I said, each output might be a face. It might be labels. It's a cat, it's a dog, it's a face, it's a bicycle, right? So that's what our input-output pairs are. But to make our lives easier, I'm going to sometimes draw it like X is a real number and Y is a real number, all right? Just so that I can draw these pictures. Everybody get that?
Why do all axes have the arrow on the top?
Oh, an arrow means that it's a vector. So I wanted to remind that it's not one number, but, right, what is an image really? An image really is 20,000 numbers, right? A million numbers. So we can write, if we wrote those million numbers in one big array, then we would call it a vector, right? What's a vector? Have you learned about vectors? Right? Yeah. A vector is a whole array of numbers, right? And this image is an array of numbers. And so I put an arrow on top is a reminder that X is not one real number. It's an array of numbers. Does that make sense?
Yes.
Good.
Thank you.
Good question. Good question. All right. So here's what I'm talking about, right? What is our input really, right? It's one big array of numbers, right? Each pixel tells you the color, right? In fact, each pixel, there's how much red there is, how much blue or yellow or brown there is. I forget what the 3 dimensions is, right? And so we're giving your machine a big array, a big vector, right, of numbers, right? Now, your brain can somehow get the light from this image, and your brain can say cat, right? But how does your brain do that, right? Effectively, your brain also has all these little pixels. It knows whether it's light here or it's dark here. And your brain somehow says cat, right? So how does the neural net from this image say cat? It's just absolutely mind-boggling that this works, right?
Jeff, I have a question.
Yeah.
So on the image there where it says like 82% cat, 15% dog, right, is that what happens sometimes when you search a picture on Google Images and you get like a random object?
Yeah. So what is going to return, the Y that's getting returned will actually probably also be a vector. It'll probably give you what percentage do you think it's a cat? What percentage do you think it's a dog, a face, or a bicycle, right? So it might give us a real number for each of these. And it says with 80% confidence, I think it's a cat, right? And 2%, I think it's a hat, right? I'm not completely convinced it's not a hat, right? Does that make sense?
Yeah, thank you.
All right, so here we have this complex XY data, and we have to define what we mean by a machine, all right? So our machine has 2 things that matter for it, right? What we know about our machine is that what it does is governed by a bunch of weights. And again, it has a vector on top. Why does it have a vector, an arrow on top? It's because it's a big array of numbers, right? What is the vector of weights? It's a huge array of real numbers, right? And what the machine does depends on, right? So here, the machine, everything we know about the machine, we write down as an array of M real numbers, right? That's what our W is. And right, each of these W's is a real value parameter, right? So let's do some examples. So suppose everything was really nice, everything was linear. So here our machine, what does our machine do? Is it the weights, the green is our machine, right? And what does the machine do? Is it takes the input, right? So remember, the input is a vector of real numbers. So I'm going to take the first real number of the input, right? I'm trying to calculate. I have my DEEF training data, right? DEEF, here's a DEEF input. And for the DEEF input, I look at what's its first pixel, what's its second pixel, what is its end pixel, right? And what do? Is I take each of those bits of information about the input, and each gets multiplied by a particular weight, right? The first pixel, how bright the first pixel is, gets multiplied by some W1. How bright the second pixel is gets multiplied by W2. And then we add it all up, right? And why do I have a W0? Because that's some constant at the beginning, right? Does that make sense? Everybody, and that, what does that give me? That gives me a line. That's why it's called linear, or a plane, right? It gives me a hyperspace, right? So here, let's do another example. Suppose the output, D now is my data example. Maybe it's the given day, right? So given today, I want to know what's the likelihood it's going to rain on day D, right? So now I know the input. How am I going to determine whether or not it's going to rain? Well, I know various things about the day, right? My first piece of data about the day tells me whether there are clouds in the sky, right? And clearly, if there are clouds in the sky, it's more likely to rain, right? So here, that tells me that W1 is big and positive, right? The more clouds there are, the more I multiply the big number here by a big positive number, the more it's going to rain, right? Maybe my second number tells me the color of the shirt the man is wearing, right? So why do I care about the color of his shirt? Well, maybe whether it rains correlates with the color of his shirt. Maybe it doesn't correlate with the color of his shirt. Well, and then what's we put in here our weights. Our weights tell us what's the effect. I put in here a big positive number if there's a correlation between clouds and it rains. And I'll put here a weight 0 if there's no correlation between the color of the man's shirt and whether it will rain, right? On the other hand, maybe that if he's wearing a white raincoat, then I say yes, then it is more likely to rain, right? Does that make sense? All right, so that's a simple example called linear regression. And finding your training data, if you have training data, finding the weights that minimizes the error is something I'm not sure I actually took a course on, but I said I used it in 2 of my co-op jobs. All right. Now we might want a more complex thing. We might not want it to be a plane. We might want it to be a polynomial, right? So we add in these extra terms, right? Our data, here's the value of our first pixel squared, and the value, this is the value of what color is the man's shirt squared. We might give them various weights as well. And in all of these cases, the output is linear in the weights. And so, right, these are hand-picked features. We decide that we're going to do linear regression on this squared term and on this squared term, right? And then any good data project will find the weights for you. All right. right, so here's a more complex machine, right? This type of machine, linear regression will find the weights for you to minimize the error. That's, if you wanted, I could teach you how to do that. It's pretty easy, right? But now we get a more complex machine. This is a crazy, weird, nonlinear machine, right? We have pixels, we have weight. The weights are the weights on the edges, and it computes somehow, right? And so let's think about how it computes. So we have, we know neurons, they fire. And so here's a picture of the brain. They're neurons that fire. And so back in the early 80s, Jeff Hinton and people said, hey, neurons are cool. Let's see if we can model computation by neurons. All right. So what does a neuron do? Each neuron sometimes fires. And when it fires, it sends a signal to its neighbors across synapses. And the synapses have different weights. And if you have a big weight, then when one neuron fires, it's going to influence other neurons to fire. If you have a negative weight, then when one neuron fires, it makes the other neuron not fire, right? So, right, so a neuron takes all these incoming messages, and when the sum of the message of the firing weighted signals reaches a threshold, right, then it fires, right? That's how the brain works. How's a neuron going to work? It's going to work in the exact same way, all right? What is the input to a neuron is going to be a whole bunch of real numbers. Well, we could say the real numbers are all between 0 and 1. We could even say all the numbers are binary, right? They're yes, I'm firing, no, I'm not firing. So in fact, let's do that. Let's assume that all our x1 through xn are binary, right? They're bits, 0, 1, whether or not it's the input is firing, right? So we feed in a bicycle here, right? We're feeding here, we have values x1 through xn. So we feed in x1 through xn, and those might all be binary, or they might be real numbers between 0 and 1, right? And here what we're saying. What is the ith one, right? The ith one might tell me, might correspond to the ith pixel, right? And it might be tell me how bright the ith pixel is, right? So here, I put up here a little picture of my pixels to remind us that each of these separate entries down here corresponds to a different pixel, and it corresponds to how bright the pixel is, right? Is everybody following this? Right? On each of these wires, we feed in how bright is the ith pixel. All right. Now, this is what I'm saying. Don't worry about color. Let's just say 0 is dark and 1 is bright. And here an example, right? x1 might be a half, x2 might be 0.3, xn might be 0.4, right? They're all brightnesses. Here I'm saying their brightness is between 0 and 1, right? Everybody good with that?
Yes, sir.
So here I feed in a possible input, right? Here I feed in x1 is 0.5, x2 is 0.3. I feed them in. All right. Then what are these? The edges, each edge has associated with it another real number. They're my weights, right? I have weight 0 through weight n, W0 through Wn. And those are just real numbers, right? And what does Wi say? It's how much does the brightness of the ith pixel influence my neuron? All right. So here's some examples. W1 might be 4. That says, right, if x1 fires, then we should fire too, right? Wn9, it's even more fire. Well, W2 is negative, which means if the second pixel is bright, then I'm going to multiply it by a -2, so I don't want to fire. All right. So we have all these weights. And what do we do with all these? I wrote all the weights down, right? Those are weights. Right here, the W0 is 8, is a constant value that gets fed in. All right, and what do? We take the values of the x values, xi, and we multiply it by its corresponding weight. We just do multiply, 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 all right? And then we add them up, right? So here is what is coming in, right? It's x1 times w1 plus x2 times w2 plus xn times wn, all added up, right? Here I just gave you an example. So you multiply these things and you add. Does that make sense? And what is my W0? It's just the constant that we put in front for good luck, right? Everybody buy that? So what does this evaluate to? Well, you plug that into the calculator, it comes out to 18.2, all right? So now what's coming into this neuron is a signal of strength 18.2. And what is that? It's the sum over all the incoming wires of the value of the wire, the input on the wire times the weight of the wire. All right, great. Now, what do I do with this 8.2, right? This is a big sum. Here, that's a sigma, means sum. Here I hear Z is my sum. It's the sum of Wi times Xi, right? Now, what am I going to do with that 18.2, right? Well, the Y, the output, is supposed to be whether I'm firing or not. It's supposed to be, is it a cat or not, right? So the output is, as I say, does the brain, the neuron fire or not? Is the picture a cat or not? Here, I've got all these slides memorized, right? Now, how might we model this? Well, we don't want our output to be an 18. We want to output, yes, it's a cat, or no, it's not a cat, right? So here, what I got here is a threshold function. See here, this is called the threshold function. What we put into it is our Z value, right? Our Z value could be 0, positive 8, it could be negative 8, right? And the output is the blue. The output is 0 or 1, right? Here's a function that on these values of Z is 0, and on these values of Z is 1, right? So if we put in, our 18 goes in, then 18 is a big positive number, and what comes out is 1, right? We say yes. If the sum is 18, then I will say it is a cat. But if the sum is negative 18, then I'm way down here. And what will I say? I will say 0. It's not a cat, right? Everybody get that?
Yes.
All right. So this is called a linear separator. It's a threshold. I don't know why they call it linear, but I guess because it's called a linear separator because the input is a linear sum, and then it separates into 0, 1, right? So this here is the linear sum, and this threshold is the separator. And that's why it's called a linear separator, all right? Now, why do we not like these? AND gates and OR gates may do this, but it's not very graceful, right? We wanted to be able to do gradient descent. So we want everything to be smooth. And does this look smooth to you? No, you fall off that cliff, you go crashing down, right? Here, if I'm in here, I get no information whatsoever because it's flat. If I'm up here, I get no information because it's flat, right? Small changes either make no difference or catastrophic difference, right? So it's not graceful. So instead of having 0, 1, yes, no, we're gonna morph it into being a little friendlier, and we're gonna say maybe so. Right? That's a piece of poetry if you didn't catch it. It's the best poetry you're gonna get from me. instead of yes, no, say maybe so, right? That's poetry. So we replace it with not 1 if it's greater than 0 and 0 else. We're going to say we're going to have 0.98 will mean, hey, I think it's true. And 0.02 will mean, no, I don't think it's true, right? So we replace the sharp threshold with a graceful threshold, right? So this is called the sigmoid function, and its equation is written right there, but you don't need to understand it. All you need to know is the following, right? If my linear sum is 18, right? Here, what's the input? It's still Z, 0 to positive big numbers, negative big numbers, right? My input is an 18. I look at 18 is a big positive number. So what do I return? Well, I would like to return 1, but I'm not going to return 1 because I need to be graceful. So instead, I return 0.98, right? Now, what happens if the sum is negative 18? Then what do I return? Well, I have, right, my Z is a big negative number, so I would like to return to 0. But in order to be graceful, I will return 0.02, right? Does that make sense? What happens if the sum happens to be 0? Well, now I don't know whether to say yes or no, right? Do I say yes, it's a cat? Do I say no, it's not a cat? I don't know. I got 0. I'm on the fence. So what do I say? I'll say, I don't really know, 50-50. I don't know if it's a cat or not a cat. I'm going to say 50-50, right? Does that make sense? All right. Any questions about this?
So you would use this for like self-driving cars, right?
Yes.
And
this
so
is well, most machine learning is now done with neural nets. There are other types of machines. As I said, there are lots of types of machines. We could talk about decision trees. We could talk about convolution networks. So, but for now, let's talk about these.
So it's could be kind of funny question, but let's say you have to. It's like the first example you talked about the grandma. That you have to stop when you see the grandma.
Right.
But then what if the grandma is giving you same number, and then nothing gives you the same number? But then what would the computer would do? No, it would not give you the same number.
Yeah. Well, hopefully, if X2 is that there's a grandma, and this tells you whether to stop or not, the weight will say, as soon as there's a grandma, put a big value on Z, which will make you stop. That's so what we want to learn.
Never the same number. Both Z will be never same. Never same number.
I don't know what you mean by same number, but
so like Z is a number that's a calculator, right?
Right.
So let's say in the case of grandmas appearing,
right?
That let's say Z is 10, and then in another case like there's no grandma, and that they also give you the Z as 10, just coincidentally.
No, X. Well, maybe when X2 says grandma, weight 2 says 10. And when X3 says grandpa, XW3 says 10. So if there's a grandma, the Z will be 10. If it's a grandpa, the Z will be 10. If it's neither, it will be 0.
Okay.
Right? So if there's a grandma and a grandpa, it'll be 20.
Okay, so there will be no, the Z will never be same number then.
Well,
possibly.
Well, no. Having a grandma and no grandpa is 10, and having a grandpa and no grandma is 10. So there's two numbers which is the same.
Okay. All right. Thank you.
All right. So now let's think about a layered neural net, right? So we have our input come in, which, as we said, the I value tells us how bright the pixel is. And the desired output, right, over here far end, we want to output, is it a bicycle, is it not a bicycle, right? And our machine is going to have all these weights, right? And when we have weights are the green W's and we have the input is the purple X, then we have to calculate what the output is. The output will say bicycle, or right? The output is going to say, yes, it's a bike with probability 0.202, and it's a cat. Probability is the cat is 2. Probability is the bike is 92, right? That's what we want our output to say, right? The correct answer is bike 1, cat 0, right? But we're not going to be perfect like that. We're going to be graceful. So it's going to say some graceful answer, right? Everybody good with that? Right? That's what it says. The machine says the probability that the input is a bike is 92%, right? And then we're going to have all these hidden layers. And we don't even know what these hidden layers mean, right? The hidden layers have no human design meaning, right? We don't say, hey, maybe this neuron tells you whether there's a wheel and this neuron tells you whether or not there's a nose. But we don't talk about noses or wheels. So we don't know what those weights are doing, all right? But somehow the meaning of these hidden nodes are learned by choosing the weights, right? It learns it automatically. Maybe it does. Maybe this node here is there a nose detecting neuron, right? And just like my brain might have, am I looking at a nose neuron? But I don't know whether my brain has a nose neuron. All right. So what are our weights? They tell us the weights on the edges. All right. So here I have input Xi, and it goes to a hidden neuron J, right? And what does the weight say? The weight says how much should the Xi influence the hidden node J, right? That's what the edge says. It's the weight, the correspondence between input Xi and hidden node J. And here I have a picture of an iceberg, right? Why do I have a picture of an iceberg? It's because icebergs are mostly hidden, right? So that's supposed to mean it's the Jth hidden node. In blue is my iceberg firing, right? Does that make sense? So we have the input in purple, does it fire? And it goes along an edge which is weighted in green, and then the hidden iceberg J will either fire or not fire, right? So now this hidden node J doesn't just have one input. It has an input from all the nodes at the previous layer, right? So all of them have their weights. And so just like we calculated before, we take a sum of for each edge, we take we multiply the X value by the weight, X value times weight, X value times weight, and we added them all up. And that gives us a Z value for J. And then through J, it goes a threshold, a sigmoid, which then J either fires or doesn't fire, right? So given all these values and all these weights, that J will either fire or not fire. And then it feeds along, right? Now we have the J's, we have this hidden layer. Does it fire or not? And it goes through these weights to say whether the next layer fires or not. And it keeps feeding. These fire or not. The weights say whether it fires at the next level, and at the next level, and at the next level, which tells us whether or not we think it's a bike. Right? Does that make sense? That is our neural net. Right? And you can see how this is a big, complicated calculation, which if you tell me the weights on all the edges, you tell me the values of the incoming X values, then I can do all this calculation to tell you whether or not I think it's a bicycle. Right? Does that make sense?
Yeah, kind of. It's just a bit confusing.
Yeah, for sure. Well, if you have any questions, we can ask him now, or we can keep cycling through these. I have more slides which give you this calculation in more and more detail, right? We go over it, like this, and then we go over it a little bit more, and then we go over it a little bit more. Any questions about it now?
Sir, how do we jump between the layers? Like,
well,
how did you go from the input to the output? Like, there's so many ones between.
All right, there's so many weights, right? So here, the blue guy, we need to get for every node and every edge, we need a number. All right. So we start off with every edge is given a weight that defines our machine, right?
Yeah.
So every edge has a green weight. Every input on this first layer, right? The X layer.
Yeah.
Those nodes are given values by the input, right? The ith pixel will tell you how bright the ith pixel is. It gives you a value for that pink node, right? So if I know the values for the pink nodes and I know the values for the green edges, I now have to calculate a value for the blue, the jth blue hidden node, right? How do I do that? Well, for every I multiply xi by the weight from I to j. I multiply those, and then I add up for every I, and that gives me a z. Then I move my z through a threshold function, and that gives me a blue value, right? Does that make sense?
Yeah.
Now I have a value for everybody in that layer, right? So now I'm coloring them red, purple, because I have their values, right? I have the purple values, so I calculate the blue values. Now I have the purple values, so I calculate the blue values. I have the purple values, so I calculate the blue values. I have the purple values, I calculate the blue values.
So in the hidden layer 1, you only highlighted one, right? One.
Yeah, that was because I was giving it as an example. Because
but they're supposed to be for all of them.
You're doing it for each of them.
Oh, okay.
Right? This is just for the jth one.
Oh, that's what I got confused about. Okay, yeah.
Oh, sorry, yeah. That's the first. That's how you do one of them, but you do all of them, right?
Yeah,
maybe I should have put this.
Yeah.
I should have done that here as well.
Yeah. Okay, now it makes sense.
Right? We're just going layer by layer. All right. Right, and that's how we know the weights. We know the input. We calculate the output. All right.
So Jeff, I have another question.
Yeah.
If you so over here, like let's say if you're playing the proof game, right, or if you're trying to sell your car to the, and you have to get approved by the government or something.
Yeah.
How would you formally prove that, like, for any of these inputs, I'd always make the correct decision?
You absolutely cannot. We don't understand these weights. We're just hacking and we're hoping for the best. In fact, but somewhat you're talking about how do we evaluate it? All right. So that's what we're trying to do now. We have a bunch of weights. We have our fixed training data, right? Our training data are capital D values in purple, right? It's the input output pairs. Here it gives us our picture. Each dot is an input X and output Y, right? Is our dot. And we want to calculate, and we also know our current machine. We have the weights of all the machine. And if I understood your question is, how do we evaluate how well this machine does, right? You wanted to do first order logic. You wanted to say for all inputs, it does great. Well, that's hard. So instead, we're going to do a weighted sum. All right.
Gotcha.
We're going to calculate the error on this data. All right. So we're going to take each of the data items. Now we got little d is the D training data. So it has a particular X value. And our supervisor gave us a particular y value, right? Now, and maybe the x value is the image of a bicycle, and the y value is 100%. This is a bicycle, right? But our machine, here's our machine. What does it give? It doesn't say 100% it's a bicycle. It only says 92% it's a bicycle, right? So there's a difference between the 100% it's a bicycle and the 92% it's a bicycle. There's a difference of 8%, right? So we're gonna subtract. Oh, here I got some numbers, right? Maybe the required answer was 9.4, but the machine doesn't give 9.4, it gives 7.1, right? So it's not the required answer. So we calculate the difference. What's the error? The error is simply the difference. The supervisor wants 9.4, we got 7.1, we subtract, the difference is 2.3, right? That's the error for this Dietz training data, right? Right, so that's, but now what about this guy here? Here, for this different training data, the supervisor wanted 6.2, but the machine gave 7.5, right? So we subtract and we get negative 1.3, right? The errors in a different direction, right? So some of these errors were wrong in the one direction and some the errors wrong in the other direction. Are we estimating too high or are we estimating too low, right? So what we're going to do is we're going to take all these numbers. We're going to take the 2.3, which is the subtracting, and we're going to take the negative 1.3, which was the subtracting, and we want them all to be errors, right? One is positive and one is negative. We want them both to be positive. So we're going to square them, right? Here we square them, and what do we get when we square them? Well, it turns out that negative 1.3 squared is 1.69. How do I know? Because I put it into a calculator. All right? I just squared them. Now, why did I square them? Right? You might ask that. Well, the one reason is if you square a positive number, it's positive. You square a negative number, it's negative. And that turns all our errors positive, right? Well, it makes them all so that they're errors. Now, another reason is we want to punish big errors more than we punish small errors, right? If you take 1 and you square it, you only get 1. You take 2, you square it, it's a little worse, it's 4. But if you take an error of 10, that's really bad, right? That's where we want to say for all, right? Remember, you wanted a for all inputs. Well, we can't do a for all, but we can say, hey, if you're ever off by 10, if one input is off by 10, then that's really bad because we're going to square it and make it 100, right? So that kind of helps us say, well, it's not just average we want, right? If you're really bad on some input, then that's really bad. So if you're bad 10 on some input, then we're going to give you an error of 100.
Gotcha.
The other reason for squaring it is because if we took absolute values, right? One thing we could do is just take the absolute value of our error, right? That would turn 1.3 into a positive 1.3. But remember about graceful, right? Absolute value signs are not graceful, while squaring is graceful, right? Remember that? So that's why we take for every one of our input data, we calculate the error, which is the difference between what the supervisor wants and what the machine gives. We take that difference and we square it. And then we add them all up. And then we get some sum, right? We add it up and we get a sum. All right? And what do we do with that sum? That's our error, right? It's the sum of all of these values, right? Does that make sense?
Yeah.
All right, so you guys tell me when we want to stop because we've run out of time. Why don't we finish this error page and then stop?
Sir, do we like cover that in 13101?
Which, this?
Yeah.
I don't think you learn about machine learning until 4th year.
Oh, okay.
That's why I'm doing it now, because you may be interested. Right?
Yeah.
So here about how do we do our error, right? We knew all of these weights. So in this graph, I know weights is a highly dimensional thing, but suppose weights was only one number. If it was one number, we say, hey, we have these weights. With these weights, we get this error, right? And maybe with a different set of weights, right? Here are two different machines, right? We have light green weights. We have dark green weights. We feed all the data through both of the machines, and we calculate the sum of the square error, and that gives us two different machines, same training data. It's going to give us two outputs, which gives us two curves, which just gives us two errors, and we calculate the error of both. And now we know what is the error for these weights, and we know what the error is for those weights, right? And so we know which of these machines is better, right? The machine with the smaller weights the machine with the smaller error is better, right? That's a better machine. And we can imagine plotting it for all weights. And what is machine learning? Machine learning is given the data, right? We calculate what this curve is, right? Given the data and given weights, we can calculate the error. And then for each weights, we know what the error is. And so what is our goal is to find the weights that minimize the data, the error, right? Our goal is to find these weights that minimizes that error. Does that make sense?
Yep.
And, right, that's all I'm saying here. And that's where we'll start next class. Any questions?
Just how are the weights themselves calculated?
How are they calculated? They're just real numbers that we're going to make small changes in.
So are the initial ones for the first run, they're assigned by humans? I'm assuming they're not.
You don't want them to be all the same, because you need to differentiate. One hidden node has to somehow start off being different than another hidden node. So they're going to be assigned some random value. And so there'll be some distribution. Maybe it starts off as a random number between -1 and +1. Those nuances, right? It probably depends on the application.
Okay, and the number of layers is based on just the machine's preference, right, for determining the answer.
Yeah, the designer of the machine does the architecture of the neural net. How many layers you have, how many nodes you have at each layer, which one have weights, where the edges are. That's all designed by the grad student sitting in the basement.
Okay, cool.
All right, everybody get that?
Yes, sir.